All right, I'm back. My lunch ran a little bit late, but getting started 15 minutes later than I thought it would. Um, so just to kind of recap what we're going over this session. Uh, so finishing up capabilities, and then login and counting, which should be quick. Um, and then it's a bunch of shared library stuff, and then finally IPC. So I'm gonna go until probably about 5 p.m. Maybe a little bit later, and depends on how hungry I get in the next couple hours. But yeah, I'll take a break for dinner, and then I'm probably gonna hop on in the evening to finish up the IPC overview, which just about 10 pages. So my goal is at the end of the session to be done with the shared library stuff. So that's 3.5 chapters. It's a lot of reading, but I think I can get it done if I go fast and don't spend too much time on topics. This morning I was kind of spending a little bit too much time poking around with things, so but that's fine. It's how you learn. So, all right, let's get started. Transformation of process capabilities during exec. During exec, the kernel sets new capabilities for the process based on the process's current capabilities and the capability set of the file being executed. So you have two sets of capabilities: the stuff that's currently running in the parent process and in the forked process, the child process, before it execs. There is the permitted, the effective, and the inheritable sets for those, and then the files that is being execed, it actually has its own set of permitted, a effective bit, single bit, and a set of inheritable capabilities. So those are merged together to create these three sets for the new process after it's exec. And the operations are here. The kernel calculates the new capabilities of the process using the following rules. So say the process is inheritable, is ANDed with the file is inheritable, and then that's ORed with the capability B set, which might be the bounding set, which we haven't talked about, which I guess I'll talk about here. There's two other sets that I've noticed with capabilities that haven't been covered yet in the chapter, but it's good that he's talking about bounding set here, because I was wondering about that. Because I saw it earlier in the procpid status file has like a bounding set, cat bound. The effective set is just the file's effective set if it exists. Oh, sorry. If the file's effective bit is set, then it takes the process's permitted, the computed permitted. If it's not, then it's just 0. And that's to support capability dumb programs that were implemented without being capability aware. Then the inheritable set is then just the process inheritable set. There's no fanciness with the file inheritable up here. Okay. In the above rules, P denotes the value of the capability set prior to the exec. P prime denotes the value of the capability set after the exec, and F denotes the file capability set. The identifier cat B set denotes the value of the capability bounding set. Note that exec leaves the process inheritable capability set unchanged. Excuse me. Capability bounding set. The capability bounding set is a security mechanism that is used to limit the capabilities that a process can gain during an exec. This set is as follows. During an exec, the capability bounding set is ANDed with the file permitted capabilities to determine the permitted capabilities that are to be granted to the new program. In other words, an executable's file's permitted capability set can't grant a permitted capability to a process if the capability is not in the bounding set. The capability bounding set is a limited superset for the capabilities that can be added to the process inheritable set. This means that unless the capability is in the bounding set, a process can't add one of its permitted capabilities to its inheritable set, and then via the first of the capabilities transformation rules described above, have the capability preserved in its permitted set when it execs a file that has the capability in its inheritable set. The capability bounding set is a per process attribute that is inherited by all children uh, yeah, by a child created via fork. A preserved across exec on a kernel that supports file capabilities. Init, the ancestor of all process, starts with a capability bounding set that's set to all capabilities, obviously. If a process has the cap set pcap, why is it pcap capability? Then it can irreversibly remove capabilities from its bounding set using the prctl pr cap b set drop operation. Dropping a capability from the bounding set doesn't affect the process's permitted, effective, and heritable capability sets. A process can determine if a capability is in its bounding set using the prctl pr cap b set read operation. More precisely, the capability's bounding set is a per thread attribute starting with Linux 2626. This attribute is displayed as cap bnd field in the Linux specific procpid task TID status file. The procpid status file shows the bounding set of the permission process and main thread. Preserving root semantics. In order to preserve traditional semantics for the root user, i.e. root has all privileges when executing a file, any capability set associated with a file are ignored. Instead, for the purposes of the algorithm shown in section 39.5, the file capability sets are notionally defined as follows during an exec. If a set user ID root program is being exec, or the real or effective user ID of the process calling exec is 0, then the file inheritable and permitted sets are defined to be all ones. Inheritable and permitted, okay. If the set user ID root program is being exec, or the effective user ID of the process calling exec is 0, then the file effective bit is defined to be set. Okay. Assuming that we are executing a set user ID root program, these notional definitions of the file's capability set mean that the calculation of the process's new permitted and effective capability set in section 39.5 simplifies to the following. So the permitted is the P prime and permitted is equal to P inheritable and the B set, and the effective is just the permitted. Okay, effect on process capabilities. So it's still bounded by the B set. That's something to be aware of. Root is still bounded by the B set. No, it's an or. It's not an and. So is it bounded? Huh. I thought this would be in an and, right? To bound this set here. If it's an or, a bitwise or, that means that it can be in the left-hand side or the right-hand side. That doesn't make sense to me. Well, it's ANDed with the permitted. Let's see if AI can answer. In this expression about Linux capabilities, why is the bounding set ORed with the inheritable? I thought for something to be bounded by a bit mask, it needs to be ANDed. The bounding set is not ORed with the inheritable set. It only negates the file permitted path. The OR is between the two different sources of the permitted caps. Okay, why doesn't it gate the inheritable as well? Okay, well, I don't quite understand these expressions, but my full grokking of them is not required to continue reading. Effect on process capabilities of changing user IDs. To preserve capability with the traditional meaning for transitions between 0 and non-zero user IDs, the kernel does the following when changing process user IDs using set UID and so on. If the real user ID, effective user ID, or saved set user ID previously had the value 0, and as a result of the changes to the user IDs, all three of these IDs have non-zero values, then the permitted and effective capability sets are cleared. If the effective user ID is changed from 0 to a non-zero value, then the effective capability set is cleared. If the effective user ID is changed from a non-zero value to 0, then the permitted capability set is copied into the effective capability set. If the file system user ID is changed from 0 to non-zero value, then the following file-related capabilities are cleared from the effective capability set, pretty much all of them. Conversely, if the file system user ID is changed from a non-zero value to 0, then any of the capabilities that are enabled in the permitted set are enabled in the effective set. These manipulations are done to maintain the traditional semantics for manipulations of the Linux-specific file system user ID. Excuse me. Changing process capabilities programmatically. A process can raise or drop capabilities from its capability set using either the cap set system call or preferably the libcap API, which we describe below. Changes to process capabilities are subject to the following rules. If the process doesn't have the set pcap capability in its effective set, then the new inheritable set must be a subset of the combination union of the existing inheritable and permitted sets. The new inheritable set must be a subset of the combination union of the existing inheritable set and the capability bounding set. The new permitted set must be a subset of the existing permitted set. In other words, the process can't grant itself permitted capabilities that it doesn't have. Put another way, a capability dropped from the permitted set can't be reacquired. A new effective set is allowed to contain only capabilities that are also in the new permitted set. So there's a libcap API that we're going to discuss with an example program. Create a cap-only environment, discover the capabilities required by a program, and then some older kernels and a summary. Libcap API, up to this point, we deliberately not shown the prototype of the capset system call, or its counterpart capget, which retrieves the process capabilities. This is because the use of the system call should be avoided. Instead, the functions in the libcap library should be employed. These functions provide an interface that conforms with the withdrawn draft POSIX 1003.1e standard, along with some Linux extensions. For reasons of space, we don't describe the libcap API in detail. As an overview, we note that programs employing these functions typically carry out the following steps. Use the capgetProc function to retrieve a copy of the process's current capability set from the kernel and place it in a structure that the function allocates in user space. Okay, use the capgetProc function to retrieve a copy of the process's current capability set from the kernel and place it in a structure that the function allocates into user space. Alternatively, we may use the capinit function to create a new empty capability set structure. In libcap API, the capt data type is a pointer to used to refer to such structures. Use the capsetFlag function to update the user space structure to raise capset and drop capclear capabilities from the permitted, effective, and inheritable sets stored in the user space structure retrieved in the previous step. use the cap set proc function to pass the user space structure back to the kernel in order to change the process capabilities. Use the cap free function to free the structure that was allocated by the libcap API in the first step. At the time of writing, work in progress on libcap ng. A new improved capabilities library API details can be found at libcap ng. Example program. In listening 8.2 on page 164, we presented a program that authenticates a username plus a password against a standard password database. Where's 8.2? Oh, that's previous one. We present a program that authenticates a user plus a password against a standard password, which is protected to prevent reading by users other than root or members of the shadow group. The traditional way of providing this program with the privileges that it requires would be to run it under a root login or to make it a set user ID root program. We now present a modified version of this program that employs capabilities with the libcap API. In order to read the shadow password file as a normal user, we need to bypass the standard file permissions check. Scanning the capabilities listed in table 39.1, we see that the appropriate capability is cap DAC read search. What is that? Gotta go back to that table. Cap DAC read search. Cap DAC read search bypass file read permission checks and directory read and execute search permission checks. So allows you to read files. Our modified version of the password authentication program is shown in listing 91.1. This program uses libcap API to raise cap DAC read search in its effective capability set just before accessing the shadow password file, and then drops the capability again immediately after this access. In order for an unprivileged user to employ the program, we must set this capability in the file permitted capability set as shown in the following shell session. So we do sudo set cap DAC read search is in the permitted set for check password caps, and then we can see it's there, and then we run it, and then we type in username password and it works. And then the code here, we just have a modify cap function, a raise cap, a drop all caps, and a main, and the main comes in, asks for username and password, we then raise cap, then we get the secret password for the username, as password, and then we immediately drop all caps because we don't need to read anymore, and then we check this thing out, we like it, okay. Okay, and then we get a password from the user, and then we crypt the password, and we do the string compare here. This might be subjected to timing attacks, but we are comparing encrypted with a encrypted form, so it probably won't be, because these are probably going to be hashes that are fixed length. Okay, makes sense. Creating capabilities on the environment. In the preceding pages, we have described various ways in which a process with the user ID 0 root is treated specially with respect to capabilities. When a process with one or more user IDs that equals 0 set all of its user IDs to non-zero values, its permitted and effective capability sets are cleared. When a process with an effective user ID of 0 changes that user ID to a non-zero value, it loses its effective capabilities. When the reverse change is made, the permitted capability set is copied to the effective set. Similar procedure is followed for the subsequent subset of capabilities when the process's file system user ID is switched between 0 and non-zero values. If a process with a real or effective user ID of root execs a program, or any process execs a set user ID root program, then the file inheritable and permitted sets are notionally defined to be all ones. If the process effective user ID is 0 or is executing a set user ID root program, then the file effective bit is notionally defined to be 1. In the usual cases, i.e. both real and effective user ID are root, or set user ID root program is being exec, this means the process gets all capabilities and is permitted and effective sets. In a fully capability-based system, the kernel would not need to perform any of these special treatments of roots. There would be no set user ID root programs, and file capabilities would be used to grant just the minimum capabilities that a program requires. Since existing applications aren't engineered to make use of file capabilities infrastructure, the kernel must maintain the traditional handling of processes with the user ID 0. Nevertheless, we may want an application to run in a purely capability-based environment in which root gets none of the special treatment described above, starting with kernel 2626, and if the file capabilities are enabled in the kernel, Linux provides the secure bits mechanism. Yay! We finally get to talk about secure bits. Which controls a set of per process flags that enable or disable each of the 3 special treatments for root. To be precise, the secure bit flags are actually a per thread attribute. The secure bits mechanism controls the flags shown in table 39.2. The flag exists as related pairs of the base flag and a corresponding locked flag. Each of these base flags controls one of the special treatments of root described above. Setting the corresponding locked flag is a one-time operation that prevents further changes to the associated base flag. Once set, the locked flag can't be unset. Okay. So we got secure bit keep caps, secure bit no set UID fix up, secure bit not no root. Keep caps is don't drop permission capabilities when a process with one or more 0 user IDs sets all of its user IDs to non-zero values. This flag is in effect only if sec no SUID fix up is not also set. This flag is cleared on an exec. Don't change capabilities when user IDs are switched between 0 and non-zero values. And then finally, no root. A process with a real or effective user ID of 0 does an exec, or it execs a set user ID root program. Don't grant capabilities. And then we have lock, secure bit keep caps. Okay, we can lock those things. Okay. The secure bit flags settings are inherited in a child created by fork. All of the flag settings are preserved during exec, except secure bit keep caps, which is cleared for historical compatibility with the PR set keep cap setting described below. A process can retrieve the secure bits flags using the PRCTL PR get secure bits operation. If a process has the cap set pcap capability, it can modify the secure bits flag using the PRCTL PR set secure bit operation. A purely capability based application can irreversibly disable a special treatment of root for the calling process and all of its descendants using the following call. Okay. After this call, the only way in which a process and its descendant can obtain capabilities by executing programs that have file capabilities. Secure bit keep caps and the PRCTL PR set keep caps operation. The secure bit keep caps flag prevents capabilities from being dropped when a process with one or more user IDs with the value set 0 sets all of its user IDs to non-zero values. Roughly speaking, secure bit keep caps provides half of the functionality provided by secure bit no set UID fix up, as noted in table 39.2. Secure bit keep caps has an effect only if secure bit no set UID fix up is not set. This flag exists to provide a secure bits flag that mirrors the older PRCTL PR set keep caps operation, which controls the same attribute. The one difference between the two mechanisms is that the process doesn't need the set cap capability to employ the PRCTL PR set keycaps operation. Earlier we noted that all of these secure... I need some light. I'm struggling to read here. Turn the light on. Earlier we noted that all of these secure bit flags are preserved during exec. Except secure bit keycaps, the settings of the secure bit keycaps bit was made the converse of the other secure bit settings in order to maintain consistency with the treatment of the attributes set by the PRCTL PR set keycaps operation. The PRCTL PR set keycaps operation is designed for use by set user ID root programs running on older kernels that don't support file capabilities. Such programs can still improve their security by programmatically dropping and raising capabilities as required. However, even if such a set user ID root program drops all capabilities except those that it requires, it still maintains two important privileges: the ability to access files owned by root and the ability to regain capabilities by executing a program. The only way of permanently dropping these privileges is set all the process user IDs to non-zero values, but doing that normally results in the clearing of the permitted and effective capability sets. See the 4 points. See the 4 points in section 39.6 concerning the effect of user ID changes on capabilities. This defeats the purpose, which is to permanently drop user ID 0 while maintaining some capabilities. To allow this possibility, the PRCTL PR set keycaps operation can be used to set the process attribute that prevents the permitted capability set from being cleared when all user IDs are changed to non-zero value. The process effective capability set is always cleared in this case, regardless of the setting of the capabilities attribute. Alright, discovering the capabilities required by program. Pretty much that entire previous section I didn't really fully grok. I read the words though. It's a lot of detail that like what I'm taking away from that section is that you can create capability only environment that doesn't have all these silly rules around like when you drop or acquire different user IDs, and then you can control the behavior of that with this set secure bits flags and PRCTL. But I doubt I will ever run into that in my entire life, so I'm going to just continue on. Discovering the capabilities required by a program. Suppose we have a program that is unaware of capabilities and that is provided only in binary form, or we have a program whose source code is too large for us to easily read to determine which capabilities might be required to run it. If the program requires privileges but shouldn't be a set user ID root program, then how can we determine the permitted capabilities to assign to the executable file with set cap? There are two ways to answer this question. Use strace. Appendix A. Oh shit. There's an appendice on strace? I doubt it's a whole appendice. No, I did appendix B already. Tracing system. They have a whole appendix? I guess it's only a couple pages. That's cool. I'm definitely going to read that. I like ptrace. I like strace. To see which system calls fail with the error eperm, the error used to indicate the lack of required capability, by consulting the system calls manual page or the kernel source code, we can then deduce what capability is required. This approach isn't perfect because an eperm error can occasionally be generated for other reasons, some of which may have nothing to do with the capabilities requirements of the program. Furthermore, programs may legitimately make a system call that requires privileges and then change their behavior after determining that they don't have privilege for such a particular operation. It can sometimes be difficult to distinguish such false positives when trying to, oops, I'm on the wrong page here. False positives when trying to determine the capabilities that an executable really does need. Use a kernel probe to produce monitoring output when a kernel is asked to perform capability checks. An example of how to do this is provided in Halin, an article written by one of the developers of file capabilities. For each request to check a capability, the probe shown in the article logs the kernel function that was called, the capability that was requested, and the name of the requesting program. Although this approach requires more work than the use of strace, it can also help us more accurately determine the capabilities that a program requires. Go kprobes. Older kernels and systems. Wait a minute, how much time are we going to spend on older kernels? Almost 3 pages? Jesus. Older kernels and systems without file capabilities. In this section, we describe various differences in the implementation of capabilities in older kernels. We also describe the differences that occur on kernels where file capabilities are not supported. There are 2 scenarios where Linux doesn't support file capabilities. Before Linux 2.6.2.4, file capabilities were not implemented. In Linux kernel version 2.6.2.4 through 2.6.3.2, file capabilities can be disabled if the kernel is built with the config security file capabilities option. This also disables the secure bits mechanism described in section 39.8. Although Linux introduced capabilities and allowed them to be attached to processes starting with kernel 2.2, the implementation of file capabilities appeared only several years later. The reason that file capabilities remained unimplemented for so long were matters of policy rather than technical difficulties. Extended attributes described in chapter 16 were used to implement file capabilities and had been available since kernel 2.6. The weight of opinion among kernel developers is that requiring system administrators to set and monitor different sets of capabilities, some of whose consequences are subtle but far-reaching, for a privileged program would create an unmanageably complex administration task. By contrast, system administrators are familiar with the existing Unix privilege model, known to treat set user ID programs with due caution, and can locate the set user ID and set group ID programs on the system using simple find commands. Nevertheless, the developers of the file capabilities made the case that file capabilities could be made administratively workable and eventually provided a convincing enough argument that the file capabilities were integrated into the kernel. The cap set pcap capability. On kernels that don't support file capabilities, the semantics of cap set pcap capability are different, subject to the rules that are analogous to those described in section 39.7. The process that has the cap set pcap capability in its effective set can theoretically change the capabilities of processes other than itself. Changes that can be made to the capabilities of another process, all of the members of the specified process group, or all processes on the system except a init and the caller itself. The final case excludes a init because it is fundamental to the operation system. It also excludes the caller because the caller may be attempting to remove capabilities from every other process in the system, and we don't want to remove the capabilities from the calling process itself. However, changing the capabilities of another process is only theoretically possible. On older kernels and on modern kernels where support for capabilities is disabled, the capability bounding set discussed next always masks out the cap set pcap capability. The capability bounding set. Since Linux 2.6.2.5, the capability bounding set is a per process attribute. However, on older kernels, the capability bounding set is a system-wide attribute that affects all processes on the system. The system-wide capability bounding set is initialized, so it always masks out cap set pcap described above. Okay. On kernels after 2.65, Removing capabilities from the per process bounding set is supported only if file capabilities are enabled in the kernel. In that case, init and its ancestors of all process. The ancestor of all processes starts with a bounding set containing all capabilities, and a copy of that bounding set is inherited by other processes created on the system. If file capabilities are disabled, then because of differences in semantics of cap set pcap described above, init starts with a bounding set that contains all capabilities except cap set pcap. There is one further change in semantics of the capabilities bounding set in Linux 2625. As noted earlier, on Linux 2625 and later, the process capability bounding set acts as a limiting superset for the capabilities that can be added to the process inheritable set. In Linux 2624 and earlier, the system-wide capability bounding set does have this masking effect, and it is not needed because these kernels don't support file capabilities. System-wide capability binding set is available via the Linux specific proc syskernel cap bound file. Do I even have that? Proc syskernel cap bound? No, cap last cap. No cap. Cap bound. It's not there. Makes sense because I have process specific bounding sets, not a global bounding set. A process must have the capsys module capability to be able to change the contents of the cap bound. However, only in the init process can turn bits on in this mask. Other privileged processes can only turn bits off. The upshot of these limitations is that the system where file capabilities are not supported, we can never give the cap set pcap capability to a process. This is reasonable since the capability can be used to subvert the entire kernel privilege checking system. In the unlikely case that we want to change this limitation, we must either load a kernel module that changes the value in the set, modify the source code of the init program, or change the initialization of the capability bounding set in the kernel source code and perform a kernel rebuild. Confusingly, although it is a bit mask, the value in the system-wide cap bound file is displayed in a single decimal number. For example, the initial value of this is, yep, okay, great. Next, using capabilities within a program on a system without file capabilities. Even systems that don't support file capabilities, we can nevertheless employ capabilities to improve the security of a program. We do this as follows: run the program in a process with an effective user ID of 0, typically a set user ID root program. Such a process is granted all capabilities except cap set pcap. As noted earlier, it is permitted in effective sets. On program startup, use the libcap API to drop all capabilities from the effective set and drop all capabilities except those that we may later need from the permitted set. Employ the call prctl prset keep caps so that the next step does not drop capabilities. Set all user IDs to non-zero values to prevent the process from accessing files owned by root or gaining capabilities by doing an exec. We can replace the two preceding steps by a single step that sets the sec bit no root flag if we want to prevent the process from regaining privileges on an exec, but must allow it to access files owned by root. Of course, allowing access to files owned by root leaves open the risk of some security vulnerability. Okay. During the reset of the program's lifetime, use libcap API to raise and drop the remaining permitted capabilities from the effective set as needed in order to perform privileged tasks. Some applications built for Linux kernels before version 2624 employed this approach. Among the kernel developers who argued against the implementation of capabilities for executable files, one of the perceived virtues of the approach described in the main text was that the developer of an application knows which capabilities an execution requires. By contrast, the system administrator may not be able to determine this information. what I really want is like a thing that like basically like when you write a program, like it starts off no capabilities and can do like no syscalls. And then you have to go in and like authorize the syscalls. I guess that'd be seccomp. But like something that is tied to the process itself. So it has to like declare, I want these things, and if I want to be able to make these syscalls, and have that data stored somewhere in the binary, and then also have it like tell the kernel, hey, I want to do seccomp or whatever to make sure that my process, this process can only do these handful of syscalls. It's like a drop syscall capability, or drop syscall function. And what's nice about that is like the process enforces it itself, but you could also read if that data was stored in the binary in some section of the binary, you could then have it read by other tools that automate that, where they say like, okay, this program is only requesting these 5 syscalls, so I'm just gonna set up a seccomp profile for it, so it doesn't even have to do it, or we can do it on the outside of the process and as well as the inside. Anyways, summary: Linux capability scheme divides privileged operations into distinct categories and allows a process to be granted some capabilities while being denied others. This scheme represents an improvement over the traditional all or nothing privilege mechanism, whereby a process either has either privileges to perform all operations or no privileges. Since kernel 2.6.2.4, Linux supports attaching capabilities to files so that a process can gain selected capabilities by executing a program. Exercise: modify the program and listing so-and-so to use file capability. I'm not going to be doing that. Next, login accounting. This is going to be a boring one. I might just blast through this whole thing without even stopping. How many pages is this? All right, we'll record where we're at now, which is 8:17, and we're at 1:57. So 45 minutes, we got about 12 pages. That's good. Login accounting. Oh God, this stuff is gonna be annoying. About 15 pages, and then we get into some fun stuff. All right, I'm gonna speed read this one because I don't really care about login accounting as a user. I'm not really a system administrator. I'm not a security administrator, SecOps or whatever. Something that they would care about. Let me get some water here. I'm going to try to read this fast, but also enunciate words clearly, understand concepts as I read, but go quickly. Login accounting. Login accounting is concerned with recording which users are currently logged into the system and recording past logins and logouts. This chapter looks at the login accounting files and the library functions used to retrieve and update the information they contain. We also describe the steps that an application providing a login service should perform in order to update these files when a user logs in and out. I will never write an application providing a login service, but good to know, I guess. Overview of the utemp and wtemp files. Unix systems maintain 2 data files containing information about users logging in and out of systems. The utemp file maintains a record of users currently logging into the system, as well as certain other information that we describe later. Sorry, my lunch is coming up. All right. As each user logs in, a record is written to the utemp file. One of the fields in this record, user, records the login name of the user. This record is later erased on logout. Programs such as who use the information in the utemp file to display a list of currently logged in users. So if I say who, that's going to be like, oh, just C0. But if I say strace summary, I think it's C, who, and then it's doing some type of open, right? Open at. So if we say, I think it's -e, open at, and then we can take this thing off. We can see all of our opens. So utemp is under var run. So cat out var run utemp. It's a bunch of binary stuff. But you can see my username there, tty1 c0, and then some other garbage. Hopefully that doesn't have my password in it. Probably not, because it's unprotected. I didn't have to sudo to do that. Yeah, if it's read everyone, then they wouldn't put any sensitive information in it. Let's see. The wtemp file is an audit trail of all user logins and logouts, as well as certain other information that we describe later. On each login, where was that? Var run utemp? Is there a, oops. Is there a LSHLA var run wtemp? Well, it's not located there. The wtemp file is an audit trail of all user logins and logouts, as well as certain other information that we describe later. On each login, a record containing the same information as is written to the utemp file is appended to the wtemp file. On login, a further record is appended to the file. This record contains the same information, except that the user field is zeroed out. The last command can be used to display and filter the contents of the wtemp file. Last. Bunch of C0 reboot stuff. And if I do the same strace that I did before, but do last, you can see, wait a minute. Oh, this is the output for it. Wtemp var log wtemp. Cat var log wtemp. Very similar. Last. Did I reboot 2 days ago? I don't remember doing that. But yeah, look, December 29th. If I do uptime, I guess I did. Something must have happened where I restarted. I don't remember doing that. Oh, I did have a glitch before stream on my workstation, yeah. Okay. Okay. On Linux, the utemp file resides in var run temp, and the wtemp file resides in var log wtemp. In general, applications don't need to know about these path names since they are compiled into glibc. Programs that do need to refer to locations of these files should use the path utemp and path wtemp path name constants defined in paths and utmpx.h rather than explicitly coding path names into programs. Costudy3 doesn't standardize any symbolic names for the path names of the utemp and wtemp files. The names path utemp and path wtemp are used on Linux and the BSDs. Many other Unix implementations instead define the constants utemp file and wtemp file for these path names, Linux also defines these names in utemp-h, but doesn't define them in utemp-x.h or paths. Okay. utemp-x API. The utemp and wtemp files have been present in the Unix system since early times, but underwent steady evolution and divergence across various Unix implementations, especially BSD versus System V. System V Release 4 greatly extended the API, and the process created a new parallel utemp-x structure and associated utemp-x and wtemp-x files. The letter X was likewise included in the names of header files and additional functions for processing these new files. Many other Unix implementations also added their own extensions to the API. In this chapter, we describe the Linux utemp-x API, which is hybrid of the BSD and System V implementations. Linux doesn't follow System V in creating parallel utemp and wtemp files. Instead, the utemp and wtemp files contain all of the required information. However, for compatibility with other Unix implementations, Linux provides both the traditional utemp and the System V utemp-x APIs for accessing the contents of these files. On Linux, these two APIs return exactly the same information. One of the few differences between these two APIs is that the utemp API constants contains reentrant versions of the few functions, while the utemp-x API does not. However, we confine our discussion to the utemp-x interface, since that is the API specified in SUSV3 and is thus preferred for portability to other Unix implementations. The SUSV3 specification doesn't cover all of the utemp-x API, e.g. the location of the utemp and wtemp files are not specified. Let me launch AI. Why are these files called utemp and wtemp? User temporarily. Who? But the who command looks at utemp, not wtemp. Okay. Okay, the utemp-x structure. Utemp and wtemp files consist of utemp-x records. Utemp-x structure is defined in utemp-x-h, as shown in listing 41. The SUSV3 specification of the utemp-x structure does not include the host, exit, session, adder v6 fields. The host, exit fields are present on most other implementations. Session is present on a few other implementations, and adder v6 is Linux specific. SUSV3 specifies the line user fields, but leaves their lengths unspecified. The int32 type data type used to define the adder 6 field of the UTEP-X structure is a 32-bit integer. Wait a minute. V6 addresses are 128 bits, bro. Don't know where you're getting 32-bit integer. Oh, there's a 4 on it. There, that makes sense. Okay. So we get the type of the record, the PID of the login process, the terminal device, suffix from the terminal name or ID field from init tab, username, host name, or remote login, or kernel version for the run level messages, exit status of the process marked as dead process, not filled in by init8 on Linux, okay. Session ID, time when the entry is made, IPv6 address, and then unused. 20 bytes unused, wow. Each of the string fields in the UTEP structure is null terminated unless it completely fills the corresponding array. For login processes, the information stored in the UT line and UTID fields is delivered from the name of the terminal device. The line field contains the complete file name of the terminal device. ID field contains the suffix part of the file name. That is a string followed by following TTY, PTS, or PTY. Last two are for system V style and BSD style pseudo-terminals respectively. Thus for terminal dev TTY2, line would be TTY2, and ID would be 2. In the windowing environment, some terminal emulators use session field to record the session ID for the terminal window. Refer to section 34.3 for an explanation of session IDs. I don't really want to go back there. Thank you. The type field is an integer to define a type of record being written to the file. The following set of constants with the corresponding numeric values shown in parentheses can be used as values for this field. Empty. This record doesn't contain valid accounting information. LVL level. This record indicates a change in system's run level during system startup or shutdown. Information about run levels can be found in the init man page. The GNU source feature test macro must be defined in order to obtain the definition of this constant from UTEP-X. Boot time. This record contains the time of system boot in the TV field. The usual author of level boot time records is init. These records are written to both the UTEP file and WTEP file. New time. This record contains the new time after the system clock change recorded in TV field. Old time. This record contains the old time before the system clock change recorded in the TV field. Records of the old time and new time are written to the UTEP and WTEP files by the NTP or similar daemon when it makes changes to the system clock. Init process. This is a record for a process spawned by init, such as getty process. Refer to the init tab manual page for details. Login process is a record for a session leader process for a user login, such as a login one process. User process is a record for a user process, ideally a login session with a username appearing in the user field. Login session may have been started by login or by some application offering a remote login facility, such as FTP or SSH. Oh, interesting. And then dead process. This record identifies a process that has exited. God, there's so much information here. Jesus Christ. UTEP and WTEP, baby. Alright, we show the numeric values for these constants because various applications depend on the constants having the above numeric order. For example, in the source code of the getty program, we find checks such as the following, so-and-so. Yeah. Records for the type init process usually correspond to invocations of getty or getty, or similar programs such as agetty or mingetty. On system boot, the init process creates a child for each terminal line and virtual console, and each child executes the get ty program. The getty program opens the terminal, prompts the user for a login name, and then executes login after successfully validating the user and performing various other steps. Login forks a child that executes the user's login shell. The complete life of such a login shell is represented by 4 records written to the wtemp file in the following order. Retrieving information from the utemp and wtemp files. The functions described in this section retrieve records from files containing the X format records. By default, these functions use a standard utemp file, but this can be changed. These functions employ the notion of a current location within the file from which they are retrieving records. This location is updated by each function. Set UX and function rewinds the utemp file to the beginning. Normally we should call so and so before employing any of the get functions described below. This prevents possible confusion that might result if some third-party function that we call has previously made use of these functions. Depending on the task being performed, it may also be necessary to call set uxxent again at the appropriate point later in the program. Okay. So it's like get utemp x entity ID and line. And they return pointers to statically allocated memory. I don't really care about these functions. I'm going to skip over them. So this is just a program that dumps the stuff out, which I already have a program that does that. Very well. Get login. Retrieving the login name, get login. The get login function returns the name of the user logged in on the controlling terminal of the calling process. This function uses the information maintained in the utemp file. Can I just call it get login? How do I make the syscall get login from the CLI? This function uses information maintained in the utemp file. The getLogin function calls tty name to find the name of the terminal associated with the calling process standard input. It then searches the utemp file for a record whose uline value matches the terminal name. If a matching record is found, then getLogin returns the ut user string from that record. If a match is not found, the error occurs. getLogin returns null. Okay, updating the utemp files and wtemp files for a login session. This is if you're writing software that is actually logging stuff in. I don't care to do that, or read an example program that does that. The last log file. The last log file records the time each user last logged into the system. This is different from the wtemp file, which records all logins and logouts by user. Among other things, the last log file allows the login program to inform users at the start of a new login session when they last logged in. In addition to updating utemp and wtemp applications providing login services, should also update last log. As with the utemp and wtemp files, there is variation in the location and format of the last log file. Few Unix implementations don't provide this file. On Linux, this file resides at var log last log and a constant path last log. Let's count that out. There's nothing there. Just a regular file. So it has the line, the host, and time. Note that these records don't include a username or ID. Set the last log file consists of a series of records that are indexed by user ID. Okay. Pretty straightforward. Summary. So I skipped a big chunk of this chapter because it's just a bunch of detail on utemp and wtemp stuff, like the API, managing the files. Like, I really just don't care about any of that. And it's detail. If I need it, I can read the man page. Login accounting records records the users currently logging in, as well as past logins. This information maintained in 3 files: the utemp file, which maintains a record of all currently logged in users; the wtemp file, which is an audit trail of all logins and logouts; and the last log file, which records the time of the last login for each user. Various commands such as who and last use the information in these files. The C library provides functions to retrieve and update the information in the login accounting files. Applications providing login services should use these functions to update the login accounting files so that commands depending on this information operate correctly. Yeah, okay. I'm good. Next page. Here we are. Something a little bit more exciting. Okay, we're on 8:33. 8:33 at 2:25. And that's because we skipped a big section of that chapter that was just gory detail on something that is not interesting at all. All right. So we got 2 chapters on shared libraries and then an introduction to IPC. I've been reading for about an hour and 10 minutes. I don't know. I don't really feel like starting to tackle this. I feel a little drained right now. This is like that afternoon downtime that I was talking about earlier this morning. Just my brain just starts slowing down. Ugh. Ooh, it's just me, myself, and I. All right. I'm gonna go to the bathroom and splash some water on my face. That helped yesterday. I'll be right back. Play some music for you here. I was just splashing water in my face, and I was thinking, man, Linux is like the craziest like hobby project there is. Like, I know it's like the biggest open source project, but it is really just genuinely like a hobbyist project, or at least it was for a while. I don't know if you can say that now with all the corporate interests, but you can tell just by all the work that was put into writing this book and all these little features and things, like all this collaboration. Like, it's just amazing all the work that's been put into this thing over the decades. I guess Linux got started in what, like 90s, early 90s was Linux development started. History of Linux, 1991. That is crazy. By 2001, Linux was just freaking dominant. Like, obviously, like Windows was dominant on the desktop, but as far as like people who did software, like everyone knew about Linux. Everyone was at least had Linux on a partition on their machine to boot into to do stuff. Like, and now, what is it? 20 years after that, it's kind of crazy to think how much has happened in the past couple decades. So 91, I was completely oblivious of Linux. I was 6 years old. Let's look at the history of Linux here. Wikipedia article. It's Ken Thompson, Dennis Ritchie, Linus Torvalds. This is not what I expected. This is amazing. Okay, here, chronology. Version 1.0. '94. So 94, I was still obviously completely oblivious of Linux. I would have been 9 years old. Barely even had a computer. I started getting into computers a little bit around, like, not just like casually. I guess it was, I don't know. I remember the internet. The internet happened around my 7th grade year, 7th to 8th grade, which would put me at about 97, 98. Should have been around here. And even at that time, I wasn't aware of Linux. I think it would have taken 99. Yeah, that's when I became aware of Linux. Slackware was the first distribution that I used. And then it's been 20, how many years? 25 years? Jesus Christ, since then. 26 years, depending on how you count it. 26 years, and it took from 91 to 99, which is 8 years, for them to get from like first public announcement to I'm aware of it. 8 years. Some important parts of my adoption of Linux. I was a Windows user through the early 2000s, and then I switched to Mac. But around 2007, yeah, that was the year. 2007 was the year that I started working professionally, and I needed to learn how servers worked. I guess throughout this entire time, I was running Linux in a shared hosting environment. So I was running Linux. I remember I got my first paid Linux box, like shared box. I got my first paid Unix. Sorry, I got my first paid Linux shared multi-user account on 2003. It was summer. No, it was fall of 2003. I had just come home from a semester at college because I entered college really early, and I was super eager to learn PHP and MySQL. My dad bought me a book. It was like an O'Reilly book with the PHP and MySQL. I think it was a O'Reilly book. No, it wasn't. It wasn't O'Reilly. PHP and MySQL book. So it had arches in it, with arches. Yeah, it's probably this one here. No, that's not it. It was this one here. But obviously it wasn't the 5th edition. I think PHP 4, maybe 5 was out. Certainly not 7. 6 was vaporware, I think. But is what I think it might have been this one here, 3rd edition. Yeah, this looks like it. And I read this thing cover to cover. My dad bought me this book, and I think this was what really, was this my first technical book that I adopted, that I read? I think it might have been. Everything else that I was reading online at the time, because I couldn't afford to buy books, and all the books that were in the library were like ancient technology. It's like you couldn't go to the library and read books there because the tech was just so old. There was nothing new. And this, I remember I went to Borders bookstore in Gainesville with my dad, and I pleaded with him to buy me this book. And he bought it for me, and I took it home, and I just read and read and read and read. And wrote little tiny programs, and I don't even know why I was doing that. I had no reason to. I wanted to create websites for my friends on the internet. I wanted to learn how to do better websites. I wanted to understand how the web worked. Because I did a bunch of like JavaScript stuff, and I didn't really like browser programming. It was really bad back in the day. But I'd done a good amount of it, and I knew that all these other websites that I was using were doing a bunch of back-end server stuff. Like, they were not front-end websites only. And to do things like authentication, you need like a back-end. You can't check password hashing in the browser. Like, the client has full control over that. They can subvert that. So I wanted to do like authenticated systems. I had also graduated from high school, and some of the people, like my guidance counselor, she was pushing me to do more database programming. And I also had like a job where it was like a it was my first little like freelance job in high school where I got paid maybe a couple $100. It was very minimal. And I deployed this Perl website for this small business that used some type of database. I forget which one. But yeah, I was doing some web stuff in high school. I liked the web. I was doing Flash. I'm going down, trip down memory lane because I don't want to read this chapter. But yeah, it is nice to reminisce about some of these older times in your life. But yeah, I'm just like amazed by like how much innovation that was going on in the 90s. It was insane. And then of course the dot-com boom and bust happened. And then I'm like in college around these years. I graduate from college. I realize I need to get on, heavy server side stuff. I'm doing front end and server stuff. And that led into the teens where I was working at data centers and cloud computing companies and finally crypto and a whole lot of other stuff. And now I'm retired. But yeah, that was like so many years of innovation from 2000. From the time at which I discovered Linux to now, it's been 26 years at least, depending on how you count it, which is 3 times the amount of time it took from Linux to be initially announced and for me to discover it. Over 3 times. It's such a beast. I remember at one point Linus was saying he imagines something else will take over, and like Linux will not be the dominant open source operating system. That he could totally imagine something like that happening. At the time when he said that, I was like, that is insane. And now looking back on it, he was so wrong. He was insane. And even he now admits, he's like, yeah, like it's like he doesn't think anything's gonna take over, because it's just so insane how much hardware and like software support is built into this project, and everything's built on it. Everything on the server, everything on, well, not everything, most things on mobile, and now on desktop, it's just having its like moment in the sun because of all these shitty commercial operating systems that are just bloated with garbage because their corporate masters can't help but like cram AI into every orifice. It's like now it's having its moment. Now it's having, and it's such a beautiful operating system for developers. Like we spent so much time trying to like get the Linux subsystem for Windows running just so that we can have a Linux-like system on a Windows operating system so that we could play video games. And then Mac users were like kind of coping with having this like busted up Unix, corporate Unix thing that no one has any insight into its development process or the source code itself, because they just do source dumps like every 6 months. So, and like you can't run like Linux native Docker containers. You have to run them in a hypervisor. It's like Docker containerization is a Linux technology, period. I mean, granted, Illumos and SunOS, like all those derivatives, like they had jails and they had zones, and BSD had jails. But containers as they exist in modern parlance, are a Linux technology. And yeah, there are Windows containers now and yada yada yada. But like when you run Docker run, it approximates 100% of the time that you're running a Linux container. And when you run them on a Mac, you're running it on Docker for the desktop, which runs in an Xhive VM on a hypervisor inside the mock kernel or whatever, and it's like super slow and broken. And I mean, they do their darndest to make it a really good experience. You have to manage its memory allocation and its CPU, and it's like this little pet that you have running on your system. And sometimes the pet dies and you have to like restart it, and like sometimes it just goes away and you try to use Docker and you can't. Whereas on Linux, it's just syscalls to the kernel. There is no kernel dying. The kernel does not die. If the kernel dies, your computer is restarting. So it's always available, and it's super lightweight. It's super fast. Do I have Docker on this machine? I don't even know if I have Docker on this machine. I mean, absent the pull time. Look how fast that is. It's so beautiful. And then say I want to like mkdir test and echo hello world into test index.html, and then a docker info inspect on nginx into less var. Is it var? I have to look up default docker volume mount location for static pages. So we do docker run it rm volume mount $pwd to user share nginx HTML, and then nginx, and then we need ports, so we'll do cat p. That doesn't seem right. Did I mess up my volume mount? Docker run, volume mount, pwd. Oh, it's pwd test. That is my bad. Three, 2, 7, 6, 9. Hey, look at that. Look at that. And I'll just background. I can't background that, can I? Yeah, I'll just do another split here. I don't even know where I created that test file. Where are you? Chapter 38. Oh, okay, that makes sense. Come on. Chapter 38. Okay, we got our file here. 32770. Let's go to hello world. Look at that. We got a website. It's just amazing how much software that we have just built on top of Linux. It is quite amazing. But yeah, I did all this. No need to spin up a virtual machine or do any of this stupid stuff. It's just built in. And then you got QEMU, which I'm only beginning to experience how awesome QEMU is. Like you can just boot up a machine in a totally different architecture. In KVM, the kernel virtual machine. Like those two technologies are amazing. That you can run virtual machines just locally with the kernel. It's built into the kernel. But yeah, the ability to boot up like a arbitrary architecture allows you to run these experiments as if you're running on that architecture. Like you can't buy all this hardware to test stuff, but you can certainly emulate it through QEMU. And there is obviously some performance loss there with QEMU, but if you want to compile a binary for a specific target architecture and you can't cross compile it for whatever reason, you can just spin up a virtual machine like in a matter of seconds. And like BusyBox Alpine Linux with BusyBox, like that's like a super lightweight distro that you can just spin it up real quick, do whatever you want, and tear it down. There's like so many different distributions of Linux that are super cool in their own little ways, in big ways. It's just so amazing. I'm just awestruck. I am in awe about how awesome Linux is. And now it's like at the core of artificial intelligence. Like all of these companies that are doing these massive server deployments, they're all running Linux, all of them. Like no one chose like an alternative operating system. Everyone went with Linux. At least with the mobile stuff, like some people are, at Apple were like, we're going to use our Mac OS garbage to create iOS, or I guess it's OS X at the time. But with AI, NVIDIA's just like, yeah, we're using Linux. I'm sure they have some other operating systems here and there, but it's just such like a silly thing to like build your own operating system at this point. So even NVIDIA, who is notoriously had a notoriously bad support for Linux, because at the time they were like graphics, and at the time there wasn't a lot of video gaming in Linux. Even they came around to supporting Linux. So it's at the heart of AI. It's unstoppable. It's amazingly unstoppable. The Linux Foundation, I don't know much about their internal politics, but I've heard some things that are critical of the foundation, and I've experienced it firsthand with the CNCF. While it's an incredible organization, and I don't want to like speak negatively of them at all, I can see how hobbyists will look at that and say like that's corporate interests gaining control over our project, you know. But it's all good, you know. I burned out on Kubernetes for a while because I just felt there's so much corporate interest involved in it. It just kind of disgusted me. Because I don't believe software should be about corporate interests competing for power. It should be about human beings expressing themselves and flourishing and creating novel things and sharing them with each other and producing economic value and creating businesses. But like corporations are just so soulless. Like these big megacorps are just like, they just suck the fun out of everything. And when you put them in charge of like the governance of these big open source projects, like you have to have like really good people doing that, really smart people. I'm gonna say that was a break there. You can't have a bunch of people who aren't in it for the love of the game. All right, I successfully burned, what was that, 30 minutes? Just ranting about Linux stuff. Hopefully that recharged my batteries here a little bit so I can get through the rest of this. All right, onward. Let's do a split right here. Okay, excited about these chapters. I am excited. Fundamentals of shared libraries. Shared libraries are a technique for placing library functions in a single unit that can be shared by multiple processes at runtime. This technique can save both disk space and RAM, both of which, I guess RAM is really expensive nowadays. So maybe these are, maybe shared libraries are more in favor nowadays because it's so expensive. It used to be that RAM and disk space were cheap, but that isn't the case anymore. This chapter covers the fundamentals of shared libraries. The next chapter covers a number of advanced features of shared libraries. Object libraries. So I'm aware of 3 formats on Linux that I've encountered. I like talking up front about my knowledge and like what I expect to learn in the chapter before I go into it. So there's the .os, which are object files that come out of the compiler. I don't really know. I think they're ELF form. I think all of these are ELF formats. They're just the raw compiler output for the functions. So you have like the symbol table, different symbols mapped to specific offsets in that file, and those offsets then contain the assembly or the machine code instructions for that function. And it's in some type of ELF format that has a bunch of metadata and stuff about it. And that's primarily used for linking at compile time, static linking. Then you have your .a files, which I've only experienced through Go. I've experienced through Go and a little bit in other areas. And those are like archives, which are groupings. It's kind of like a tar, if I'm getting this right, of like multiple object files. They're kind of like a container format. And that's what the .a is, like an archive. So it's like this archive has a bunch of compiled .os that you can statically link against. And again, the A's are statically linking. Then you have your .sos, which are shared objects, which are the dynamically linking object files. And those are just littered on your file system at runtime. And when you run a program, it will DL open and find symbols in those dynamically linked libraries, and then you can call those specific symbols that you find in the libraries, assuming you understand that, assuming you have the header files and you understand the arguments and everything, and you follow the right calling convention. You can just call into those dynamically linked objects. And I guess the other format would be just like a regular executable that can run, that has a main, has some type of entry point, an underscore start entry point, and there's a static linker that the compiler will call to link together stuff at compile time, and there's a dynamic linker that will be invoked at runtime by the program itself to discover where those shared objects are and to pull them into its address space so it can call things. And both the static and dynamic linkers do these things called relocations, which I really don't understand. I tried understanding at one point, but basically like you have these hard-coded numbers in the compiled output for where certain things are, like offsets into different areas of stack and other parts of the binary. And when you link, you have to like move those things around, and so you have to update all those references. So I think that's what relocations are. So hopefully we get into some of that, because I'm not really, I read a little bit about relocations maybe about 8 or 9 years ago, and I didn't really fully understand it. So yeah, that's my understanding of shared libraries, or libraries in general, and shared libraries specifically. And then of course there's DLLs on Windows, but we don't need to talk about that. All right, one way of building a program is simply to compile each of its source files. I guess that's the other thing I should mention is like object files have like a 1-to-1 to C source files. So every C source file that you're compiling, it generates like an object file. Whereas an archive can be like multiple of those. One way of building a program is simply compile each of its source files to produce corresponding object files, and then link all these object files together to produce an executable program like so. So you got cc, where's the -g flag? I don't know my compiler flags. I'll be upfront about that. Man gcc -g. So many flags. Okay, here. Can you go away, please? Debugging options, G. Dash. I'm just gonna ask AI. The man page on that GCC is ridiculous. cc-g-c prog.c. mod1.c, mod2.c, mod3.c. Explain these flags. So C is compile. So you're compiling the C programs into their object code. And then -o is the output file. So you're compiling an executable in the second line. The -g is the thing, I don't know what. Generate debug information. Okay. It just says put debug symbols into the binary, dwarf or whatever. Alright, linking is actually performed by a separate linker program LD. When we link a program using the cc or gcc command, the compiler invokes LD behind the scenes. On Linux, the linker should always be invoked indirectly via gcc. Since gcc ensures that LD is invoked with the correct options and links the program against the correct library files. In many cases, however, we may have source files that are used by several programs. As a first step towards saving ourselves some work, we could compile these source files just once and then link them into different executables as required. I've done that with the book source code here on some of the exercises. Although this technique saves us compilation time, it still suffers from the disadvantage that we must name all the object files during the link phase. Furthermore, our directories may be inconveniently cluttered with a large number of object files. To get around these problems, we can group a set of object files into a single unit known as an object library. This is .a, I think. Object libraries are of two types, static and shared. Shared libraries are the more modern type of object library and provide several advantages over static libraries, as we'll describe in section 41.3. I think there's .a's. If I go find and root, name star.a to devnull. Yeah, there's lots of .a's. Plang's got some stuff. There's lib32.a's. There's static linking. Got C++, standard library, atomics. Bunch of Qt stuff. Yeah, there's a bunch of stuff here. Valgrind, the Go, of course. This is what I was telling before. Most of my experience with .a's was Go. libc has a .a. Plenty of .a's on this system. Okay. Aside from including debugger information when compiling a program, and aside, in the CC command shown above, we use the -G option to include debugging information in the compiled program. In general, it is a good idea to always create programs and libraries that allow debugging. In earlier times, debugging information was sometimes omitted so that the resulting executable uses less disk and RAM, but nowadays disk and RAM are cheap. that is no longer true. RAM's not cheap. In addition, on some architectures such as x86-32, the fomit frame pointer option should not be specified because it makes debugging impossible. It doesn't make it impossible, but it makes it really freaking hard. On some architectures such as x86-64, this option is enabled by default since it doesn't prevent. On some architectures, this option is enabled by default since it doesn't prevent debugging. Yeah. For the same reason, executables and libraries should not be stripped of debugging information using strip. Static libraries. Before starting our discussion of shared libraries, we begin with a brief discussion of static libraries in order to make clear the difference and advantages of shared libraries. Static libraries are known as archives, were the first type of library to be provided on Unix systems. They provide the following benefits. We can place a set of commonly used object files into a static library file that can then be used to build multiple executables without needing to recompile the original source file when building each application. Link command becomes simpler. Instead of listing a long series of object files on the link command line, we specify just the name of the static library. The linker knows how to search a static library to extract the objects required by the executable, creating and maintaining a static library. In effect, a static library is simply a file holding copies of all the object files added to it. The archive also records various attributes of each of the component object files, including file permissions, numeric user and group IDs, and last modification time. By convention, static libraries have the names of the form libname.a. A static library is created and maintained using the AR command, which has the following general form: AR options archive object file ... boom, boom. The options argument consists of a series of letters, one of which is the operation code, while the others are modifiers that influence the way the operation is carried out. Some commonly used operation codes are the following: replace, insert an object file into the archive, replacing any previous object file with the same name. Insert an object file into an archive, replacing any previous object file in the same name. This is a standard method for creating and updating an archive. Thus, we might build an archive with the following commands: gc bam, AR, replace, bam, and then we remove the .os. As shown above, after building the library, we can delete the original object file if desired, since they are no longer required. Table of contents: display a table of contents of the archive. T. Let's try doing that with one of these Go ones. Here we go. That's not my home directory though. I wanted one in my home directory. There's got to be more than this stuff. Test data. All right, well, we'll do libz here. ARTV, this guy. Oh, so they do have user IDs and group IDs. Interesting. Display a table of contents of the archive. By default, this just lists the names of the object files in the archive. By adding the v verbose modifier, we additionally see all of the other attributes recorded in the archive for each object file, as in the following example. The additional attributes that we see for each object are, from left to right, its permissions when it added to the archive, its user ID and group ID, its size, and the date and time at which it was last modified. Fascinating. I don't know why I would need all that information. Delete a named module from the archive, as in this example. Using a static library, we can link a program against a static library in two ways. The first is, I guess it makes sense that this would be user 0. I'm curious if the stuff under my home directory is also user 0 here. So maybe we take these two guys. I'll do one of these. Do this one first. And we'll do that. That is also root. And then ARRTV. This one is not. And if I do, it's a GOX file. Name longer than 16 bytes. .gox. Go executable. Interesting. I've never ran into that. Very, very interesting. So we're using the static library. We can link a program against the static library in two ways. The first is to name the static library as part of the link command, as in the following. Alternatively, we can place the library in one of the standard directories searched by the linker, and then specify the library name using the L option. So we say demo, libdemo.a. If the library resides in a directory not normally searched by the linker, we can specify that linker should search this additional directory by using -L option. Although static library may contain many object modules, the linker includes only those modules that the program requires. Having linked the program, we can run it in the usual way. Overview of shared libraries. When a program is built by linking against a static library, or for that matter without using a library at all, the resulting executable file includes copies of all of the object files that were linked into the program. Thus, when several different executables use the same object module, each executable has its own copy of the object modules. This redundancy of code has several disadvantages. I'm curious, when I link a .o file that has, say, 1,000 functions in it into my program, but I only use one function, and that function has no dependencies on the other 999 functions, does the compiler include all 1,000 in the resulting executable? If not, how does it do that? Be brief in your description. Wait a minute. Okay, so I guess the compiler will figure it out, but if you don't give it special flags to the linker, it won't. Okay. Let's start from up here. I forgot where I left off. This space is wasted storing multiple copies of the same object module. Such wasted space can be considerable. If several different programs using the same module are running at the same time, then each holds separate copies of the object modules in virtual memory, thus increasing the overall virtual memory demands on the system. If a change is required, perhaps a security fix or bug fix to an object module in a static library, then all executables using that module will be relinked in order to incorporate the change. This disadvantage is further compounded by the fact that the system administrator needs to be aware of which applications were linked against the library. Shared libraries were designed to address these shortcomings. The key idea of a shared library is that a single copy of the object module is shared by all programs requiring the modules. The object modules are not copied into the linkable executable. Instead, a single copy of the library is loaded into memory at runtime. When the first program requires a module from standard shared library is started, when other programs use the same shared library and later executed, they use the same copy of that library that's already loaded into memory. The use of shared libraries means that executable programs require less space on disk and when running in virtual memory. Although the code of a shared library is shared among multiple processes, its variables are not, obviously. Each process that uses the library has its own copies of the global and static variables that are defined within the library. Shared libraries provide the following further advantages. Because overall program size is smaller, in some cases programs can be loaded into memory and started more quickly. This point holds true only for large shared libraries that are already in use by another program. The first program is loaded to load the shared library will actually take longer to start since the shared library must be found and loaded into memory. Since object modules are not copied into the executable files but instead maintained centrally in a shared library, it is possible, subject to limitations described in section 41.8, to make changes to the object modules without requiring programs to be relinked in order to see the changes. Such changes can be carried out even while running programs or using an existing version of the shared library. The principal cost of this added functionality are the following. Shared libraries are more complex than static libraries, both at a conceptual level and at a practical level of creating shared libraries and building the programs that use them. Shared libraries must be compiled to use position independent. This is the relocation thing. Position independent code described in section 41.4.2, which has a performance overhead on most architectures because it requires the use of an extra register. Symbol relocation. Oh, maybe these are different concepts. Symbol relocation must be performed at runtime. During symbol relocation, references to each symbol, a variable or function in a shared library needs to be modified to correspond to the actual runtime location which a symbol is placed in virtual memory. That makes sense. Because this relocation process, a program using a shared library may take a little more time to execute than its statically linked equivalent. One further use of shared libraries is as a building block in the Java native interface, JNI, which allows Java code to directly access features of the underlying operating system by calling C functions within a shared library. For further information, see so-and-so. I'm not interested in Java. Sorry, I'm behind a page. My bad. Creating and using shared libraries at first pass. To begin understanding how shared libraries operate, we look at a minimum sequence of steps required to build and use a shared library. For the moment, we'll ignore the convention that is normally used to name shared library files. This convention, described in section 41.6, allows programs to automatically load the most up-to-date versions of the library they require, and also allows multiple incompatible versions of so-called major versions of the library to coexist peacefully. In this chapter, we concern ourselves only with the executable and linking format ELF shared library, since ELF is the format employed for executables and shared libraries in modern versions of Linux, as well as many other Unix implementations. ELF supersedes the older a.off, out, and coff formats. So coff is used by Windows, and because of Microsoft's influence in developing EFI and Secure Boot, it's all infected with coff stuff as well. So UEFI and coff uses coff for all of its stuff. UEFI and Secure Boot. Creating a shared library. In order to build a shared version of the static library created earlier, we perform the following steps. So we do the GCC this time instead of CC. I wonder why I switched to GCC. We say give me the debug symbols, and then we pass an FPIC, which is position independent code, maybe? I don't know. We give it warning all, and then we give it the 3 C files. So these are going to generate our O files. And then we compile our shared library by saying GCC, again, debug, we say -shared, and then we do -o libfoo.so, and we give it all of our object code. The first of these commands creates the 3 object modules that will be put into the library. We explain the CC fpic option in the next section. The CC shared command creates a shared library containing the 3 object modules. By convention, shared libraries have the prefix lib and the suffix .so for shared object. In our examples, we use the GCC command rather than the equivalent CC command to emphasize that the command line options we are using to create shared libraries are compiler dependent. Using a different C compiler on another Unix implementation will probably require different options. Note that it is possible to compile the source files and create the shared library in a single command. So we say the same thing, but we give it the C files instead of the object files. However, to clearly distinguish the compilation and library building steps, we'll write it as 2 separate commands in the examples shown in this chapter. Unlike static libraries, it is not possible to add or remove individual object modules from a previously built shared library. As with normal executables, the object files within a shared library no longer maintain distinct identities. Yep. Here's my understanding as well. Position independent code, the FPIC option specifies that the compiler should generate position independent code This changes the way the compiler generates code for operations such as accessing global static and external variables, accessing string constants, and taking the address of functions. These changes allow the code to be located at any virtual address at runtime. This is necessary for shared libraries since there is no way of knowing at link time where the shared library code will be loaded into memory. The runtime memory location of a shared library depends on various factors, such as the amount of memory already taken up by the program that is loading the library, and which other shared libraries the program has already loaded. On Linux x86-32, it is possible to create a shared library using modules compiled without the fpic option. However, doing so loses some of the benefits of shared libraries since pages of the program text containing position-dependent memory references are not shared across processes. On some architectures, it is impossible to build shared libraries without the fpic option. In order to determine whether the existing object file has been compiled with the fpic option, we can check for the presence of the name global offset table. In the object file symbol table using either of the following commands. So if I do like something like ls-la, so these are under user lib, there's a bunch of stuff. I'm just gonna say user lib. So user lib grep for .so. Okay, there's plenty of stuff here. So what I'm gonna do is say, hey, sorry, quit. Please quit. Find user lib name is going to be lib star dot so star. Okay, so give us all of our library files, and then while read line do echo $line done. So that'll give us the same output, but we have it in a loop now. We can go in and say echo line, and don't put the new line there. Actually, no, I'll say echo line, but then I'm also gonna do a subshell here, and I'm gonna quote the whole thing so that we don't get any new line monkey business going on. And in here, actually no, quoting does put the new line monkey business in. Alright, so here we say nm, or we just use read elf s $line, and we're gonna grep for under global offset table. Actually, I'm gonna pipe that into temp scan. And then I'm gonna launch into the terminal, run less on this, and we'll search for global. So a lot of these are not position independent. So if I cat out temp scan and we grep for underscore global. Okay, so like things like lib standard C++, that is position independent because it has a global offset table. Objective C, I'm surprised to even see that on my machine. But I guess it comes with GCC because they have a Objective C front end. What about libc, libatomic? Libc is not position independent. Okay, libgccs, libatomic, libsan, libasin. Let's say, why is libc on my computer not position independent? Okay. Conversely, if either of the following equivalent commands yields any output, then the specified shared library includes at least one object module that was not compiled with fpic. So if we just do read elf dump lib c.so. Okay, I gotta find it under user libc.so .6, and then I'm gonna say, hey, grep for text rel. So it doesn't have text rel, and it doesn't have global offset. Sorry. Yeah. The string text rel indicates the presence of an object module whose text segment contains a reference that requires runtime relocation. We say more about nm readelf and objdump commands in section 41.5. Using a shared library. In order to use a shared library, two steps must occur that are not required for programs that use static libraries. Since the executable file no longer contains copies of the object files that it requires, it must have some mechanism for identifying a shared library that it needs at runtime. This is done by embedding the name of the shared library inside the executable during the link phase. In ELF parlance, the library dependency is recorded in a DT needed tag in the executable. The list of all the program's shared library dependencies is referred to as its dynamic dependency list. I think you can do like LDD, like to find that, and you give it like bin bash, and it's like, these are my dynamic dependencies. At runtime, there must be some mechanism for resolving the embedded library name, that is, for finding the shared library file corresponding to the name specified in the executable file, and then loading that library into memory if it's not already present. Embedding the name of the library inside the executable happens automatically when we link our program with the shared library. So we got GCC, gwall, o, prog, c, so. If we now attempt to run our program, we receive the following error message. Error loading the shared libraries. libfoo so cannot open shared object file in this child directory because it's not on our linking path. This brings us up to the second requirement step, dynamic linking, which is task resolving the embedded library name at runtime. This task is performed by the dynamic linker, also called the dynamic linking loader or the runtime linker. The dynamic linker is itself a shared library named LD Linux SO2, which would be this guy. Which is employed by every ELF executable that uses shared libraries. The path name lib LD Linux SO2 is normally a symbolic link pointing to the dynamic linker executable file. This file has the name LD version, so where version is the glibc version installed on the system, for example, LD 211.so. The path name of the dynamic linker differs on some architectures. For example, Intel architecture dynamic linking is lib. Yeah, okay. The dynamic linker examines the list of shared libraries required by the program and uses a set of predefined rules in order to find the library files in the file system. Some of these rules specify a set of standard directories in which shared libraries normally reside. For example, many shared libraries reside in lib and userlib. The error message above occurs because our library resides in the current working directory, which is not part of the standard list searched by the dynamic linker. Some architectures, including x86-64 that I'm running, support execution of both 32-bit and 64-bit programs. On such systems, the 32-bit libraries reside in starter lib, and the 64-bit libraries reside in lib64 subdirectories. Makes sense. The library path environment, LD library path, and what's the LD load? Isn't there like an LD load environment variable? Just Google for LD load. LD preload. Oh, so it actually takes precedence over symbols in the main executable. That's kind of crazy. That means you don't have to be dynamically linking to a thing to like load over it. As long as it's in that library. I'd like to try that out. I'm going to say t add project tlpi attempt to override a function defined in the same. Let me just do it. So jump to tlpi. We're going to mkdir chapter 41. Chapter 41. I'm gonna go back here so get status. Git add chapter 38. But I have all that test stuff in there. Let me go into there. Make sure that's clean. RMR test. cd dot git add chapter 38. Git status. Git diff cached. Looks good to me. Then we say vim readme. I need to get us up to speed here with like our latest. So we went 38, 39, 40, and now we're on 41. So these are going to be programs. Typoed that, my bad. And here, just go back over to here, pull this down, and 39 was, oops, capabilities, login accounting, and then fundamentals of shared libraries, git add readme, git dc, git cim finish chapter, I would say 38, 39, 40. Yeah, oops. Go back here, put it in quote. Git show stat. Yep. Git status mkdir 41. Find name makefile. rsync avzci from chapter 29 into chapter 41. cd into there. We're gonna make clean in here, obviously. Don't need that. Vim.cling.d. I'm just gonna change that to be chapter 41. Not that I need it, but it's nice to have. RM exercises. RM star.c. So we got zig, yeah, got everything. Okay, Vim makefile. That should be fine. Yep. Looks good to me. Okay, git status. Okay. Vim, we're gonna say test linking override .c. Then here we're gonna have a main. The main can just be empty here. I'll include standard lib.h for that. Okay, and then in here there's gonna be I'm gonna declare a function foo. So void foo, and it's gonna have just a printf. So we're gonna have standard IO, and we're gonna say in here called from main binary. That'll be our foo, and then we just say foo here. So if we make this up regularly, then build, it just says, hey, call from main binary. I do need to add the new line here, so I'll add that there. Bam. And then CP, I also need to link against this library. So vim test linking override. We'll say void bar. Foo and bar. And then if I make this now, it's going to say, hey, you got a reference bar. So I need to create my lib. So we say libtest.c. Sorry. And here we're just going to have foo. I'm just going to read in the test. Oops. Read in test linking override. Why does that not want to read in? Read in test linking over. There we go. And we just have foo and bar here. This is called from the lib. Same thing here. Bar. And I'm gonna say bar here. And foo here. is standard pound include standard io.h. Okay. All right. I'm gonna rm build.zig and why not clang d? I don't care about that. And make file. I don't want to build star. Okay. Vim build.sh mkdir build, and then we're going to say gcc gc as test underscore, what's the name of this? Jump to chapter 41 slash LA. This guy. So hey, build that guy. First, I got to build my library. So this is gonna be dash C here. It's gonna be dash O. Build test linking override. So in here we say, hey, we're gonna compile the libtestc. That'll give us a libtest.o. We'll give this guy fpic and WAL. Why not? WAL. And then this needs to be a shared. Can I do dash O on this? Yeah. I think I do dash O build libtest.o. And here I'm going to say set dash O EA. What are these? Help set O EAX, I think is pipe fail. EUX. U. We'll say set dash X. Yeah, I don't want to do that. Okay, we'll do that. Jump to 41. Okay. EU pipe fail. I think that's what I do. Make their build. This one I don't care about. Or true. So we do GCC O build, so it builds our thing there, and then this guy is going to be libtest.so. We have to say shared lib, and then we'll give it build libtest.o. And then finally, our binary, we're going to say linking path build /build, I should say, and link against test. I think that's how you do that. Oh, let's give it a shot. Let's run our chmod plus x on build.sh, and then we /bang that. And then I want 2 to go to dev null. Okay. So we got our libtest O. Let's just try running that and see if that succeeds. I don't want to like confuse the output of these commands. So let's run our build script again. So that thing works. So we were able to compile our C into our libtest.o. And if we read elf symbols of build libtest, we can say, okay, we got our foo and our bar and a bunch of stuff. Okay. Then in here, we're going to say, okay, take the libtest o. We don't need to say wall because there's no warnings because it's not compiling anything. And we don't want to see C because we're not compiling. Are we? No. But we do want to say -o. And we want to say shared. Okay. And do I need fpic? No, I don't. The assumption is that that is already known to be fpic. So let's go ahead and run build again. Why does that not want to do dot? There we go. Oops. Dot. There we go. Okay, so it was able to do that now. So the final step is say, hey, I'm going to build my main program. Cannot find. Sorry, I messed up the flags here. Needs to be like that. Yep. There we go. And if I run build test, it's not going to find it because it can't find the library. But if I run LDD on it, it'll say, hey, I want libtest. It's not found. So I can say export. That's building. Let's go to running the test. Say export. Well, maybe it should be another jump 41. We'll say vim run.sh, and then this one will be where we export. Export ld library path is equal to ./build. So now it'll be able to find it, and then we run build test linking override. And if we chmod +x on run.sh, and then we do that. So we called. Okay, so I need to fix our C. So that would be test underscore this guy. And this needs to be foo. Foo was called from main binary. So I'm going to rebuild and rerun. So foo is called from the main library and bar is called from the lib. And then in here, I want to try, I'm going to say echo running normally. And I'll do like running normally. And then I'll do an echo down here just to separate things out. And running with LD preload. So I'm going to export LD preload. And I think I just give it the path, right? What's an example here? No, it's specific SO. Let's just try it with the path. All right, let's run. So here I have to say /libtest.so. gonna put this instead of as an export. I'm gonna put it just as like that. Same thing with this one. Okay. Okay, maybe I need to do dollar $PWD here. Nope. All right, I'm gonna do this thing. Tree dot a tree. I thought I had tree. Oh no, I have ls lt dash. Or just say lt. And then I'll cat out test linking override, cat out libtest.c, cat out build.sh, and cat out run.sh. Grab all of this and say I want to override the mains foo with the one in the library here. Yeah, that's not something you can override. That makes sense. So what we'll do is like vim up lib test. I'm gonna get rid of bar here, and then vim up. This is gonna be test, and get rid of bar here. Get rid of the foo's definition. Just have it forward declared there. Then printf main hello world. And forgot a semicolon here, forgot my F. And we'll do that. And I want to go into my lib now and say printf. I'm not going to have a dependency on standard IO. This will be int, or it doesn't matter really, but int printf. Actually, it does matter. Let me get the exact prototype, which will be this. Say external all of them. Now you go away. Int printf const char star pointer variadic defined here as here. We're just gonna write the format. Write. And this will be from the pound include Unix standard.h, and then the right in here, I need a semicolon there. This guy is gonna take in some FDs and stuff, so we can assume. Sorry, I just need to move that down here. I'm gonna actually just get this guy a little more room here. It can assume the standard out file now, and then it writes a format, and this will be strlen of format. So that's, then this needs to be down here. That. Now this guy needs strlen. I can just compute. No, I can't compute the length there. So I need pound include standard lib.h string string.h, I think it is. And then return 0, or return, I can just return whatever right returns. Okay, so I have my own printf that just prints out the format. I don't want to take too many dependencies here. Maybe this will be fine. C type dot H. Okay, so the idea being that if you call foo, it's going to use a printf, but then the main's printf is also going to be affected. And the way we tell is that it's going to be called on to be uppered. So here, let's say to upper, like that. And then this is going to complain because it doesn't return, it mutates. So we'll say here to upper. Sorry, stir to upper. Well, we'll give it a shot. Let's see what happens. Because that's just a warning. Okay. And then test here. We have our foo. We're going to do a regular printf. Okay. So let's rebuild.sh and run. Foo. Call from the lib, main, hello world. That's a problem. Because foo, I think what I need to do is say libtest.c, have this thing be underscore underscore printf, and then printf just calls into underscore underscore printf with format. And of course this has to come after this, like that. And then here it's going to call underscore underscore printf. Build.sh, run, oops. Libtestc. We need to return here, like that. Yeah. Build.sh, run. Hey, we got a segmentation fault. Okay. I think I don't know why we got a seg fault there, but I think it's because we're using printf. I want to be able to override printf, but I don't think I can do that while I'm using it. So I think I'm getting right from Unix standard.h. So if I do that, what file? Yeah, it's Unix standard.h. So I'm just going to use write. And this thing I'll just ignore. So we have our own printf that just takes in a char star out, out, out. We'll do this as a prefix. We'll write 3 bytes there. And then we write out. Sterlen out is not. So we have to write our own sterlen. There we go. I don't need to extern these because they are local. Incompatible redeclaration of library function. How is that incompatible? Let's go down here, man printf, and we'll search for, no, not the command, the library function, man3 printf. Well, this thing takes in a const char. That's different. Integer printf const char format dot. Sorry, const. Fine, we'll take a const char here. Happy? All right. Cool. Let's try building that and running it. Hopefully we don't get a seg fault. Build.sh and run. Hey, look at that. Bang bang, foo call from lib. Cannot open shared object file, no such directory. Okay. We'll take the LD library path as well. Like that. See the main, when it calls foo, when it calls printf, I want it to get swapped out. Because printf is a symbol that's in a shared library that's on the path. I want it to use my printf, not the one that's provided by the standard library. So this is almost there. Build, run. It's just I want to get 2 exclamation points before this main. So that they require LD preload. I have a C function that calls printf. I want to have LD preload override the standard lib printf. How do I do that? Maybe it's the way I'm compiling it. So I say GCC shared. I guess I could just do like they're suggesting as one command instead of doing it as two like the book says. So shared fpic wall o libtest, and then this will be libtest.c. And I don't know if I need that LDL or not. Build set sh run. Let's try adding that LDL cholesterol. Build run. Still not working. Okay, I'm gonna drop that. Let's do another dump of here. LT, and I'll cat out. First, I'll cat out libtest, and then I'll cat out test linking, and then I'll cat out the build.sh, and then I'll cat out run.sh. And then I'll actually build.sh, and I'll run it, and we'll see the output. Okay. I want to get this to work, but doesn't seem like it's going to. I'll say, please use my code for the examples, not your cooked up code. So we have our size t stir len, char star, turn size t, keep your implementation name, looks good, versioned alias needs to go up here. Oh, and then I get rid of this printf, okay. So this is semver printf. It's printf glibc25, and then foo calls that, okay. Build.sh. What is this under? User, or we say ldd libc, or ldd bin bash, and we can say, hey, just run the user libc .so.6. Sorry, not dot slash slash. This is 242. Read elf for that will be sorry. libc.so.6 grep for printf. Yeah, here it is. It is this right here. Vim up or foreground, I have foreground, vim up the libtestc. I think there's two @ signs. I think that's the difference. Build.sh. Damn it. Oops, bring this back. Build.sh, run.sh. Let's hit up Gemini. I have the following test program. I am trying to override printf in the main function with a printf that I provide via ld preload. Below is, or here are all the files and the output that shows that printf from the libc is still being ran. Tell me how to fix this. Okay, let's try this one more time. We'll do lt cat test cat libtestc cat build.sh cat run.sh, and then I build.sh and I run.sh, and I grab all of this and just dump it into here. Hopefully Gemini is smart enough to figure it out, because I'm not. Ah, that's true. That is true. All right, let's just do puts then. Because I did see, I dumped this. I did a read elf on build this thing, test linking override. Sorry, read elf. Yeah. And you see how it's doing puts, but it's not doing printf. So I need to go back into my libtest and do a puts here. So how do you do puts? We'll do man puts. It adds the trailing new line. Oh, and I'm not even building this thing anymore. So I need to say wall and then f no built-in. Don't know how that quite works. Build.sh and run.sh. Hey, but I did it for both of them. Okay. So if I do my LD library path as user lib here first, and then build, I think that would do it. No. There we go. Oh no. What was it called? No. F no. Built in. L test. I'll do L C. Let's try that. Build sh run. Ha. I got it. Finally. Just had to figure out the right flag. So I had to explicitly link against libc here. Because I'm saying link against libc and libtest. And this prevents the optimization where it swapped the printf call for puts. And then here, I say, hey, just, this is where the libtest is. But in this one, I say, and actually preload the libtest, which overrides both. Let me say both calls are prefixed with to demonstrate that lib tests printf. Just do it like this. Libtest printf. Let's inspect libtest again. Let's do one more test here. Vim test here. I'm gonna call a bar too. Bar. Vim lib test C. Let's do a bar here. We're gonna use the printf symbol. We'll say bar. Call from the lib using printf. And we'll say here using underscore printf. And here we're going to say build.sh. Oops. Build.sh. Run. Fascinating. Because bar wasn't linked, the shared library didn't have LC. If we do that, build, /build.set sh run, it's still not there. Okay, so it's using the printf from libc instead of its own printf. Is that a for declaration thing? Yeah, I wouldn't actually want this to link against libc. I think I want no built in on this as well. Build.sh run. Okay, now it's doing it correctly. Is that no built-in flag? I need to fix the typo I have here. But demonstrate, only one call is prefixed with which demonstrates that the standard lib printf is otherwise used. Say that. All calls are prefixed to demonstrate that libtest printf overrides the printf, the standard lib printf, in both the library, in both libtest and main. There we go. And I'll right quit this. Close out these. That took a while as a bit of a detour, but I'm happy that I did it because I did learn a few things about LD preload. Okay, that was a bit of a sidetrack there, but I'm happy that we did it. All right, let's continue reading. I think we're at LD library path here. Let's start at the top. The LD library path environment variable. One way to inform dynamic linker that the shared library resides in a non-standard directory is to specify that directory as a part of a colon-separated list of directories in the LD library path environment variable. Do I have that set in like the shell by default? Echo $LD library path? No. Cat run this. I just want to copy and make sure I got the right thing. echo dollar that. It's not set normally. Okay. Semicolons can also be used to separate the directories, in which case the list must be quoted to prevent the shell from interpreting the semicolons. If LD library path is defined, then the dynamic linker searches for the standard library in the directories in it lists before looking in the standard library directories. Later, we'll see a production application should never rely on LD library path, but for now, this variable provides us with a simple way of getting started with shared libraries. Thus, we can run a program with the following command. The bash, corn, and born shell syntax used in the above command creates environment variable definition for the process executing This definition tells the dynamic linker to search the libraries in dot the current working directory. An empty directory specification in the LD library path list is equivalent to dot the current working directory, but note that the setting LD library path to an empty string does not achieve the same result. We avoid this usage. Static linking and dynamic linking contrasted. Commonly, the term linking is used to describe the use of the linker LD to combine one or more compiled object files into a single executable. Sometimes the term static linking is used to distinguish this step from dynamic linking, the runtime loading of shared libraries used by an executable. Static linking is sometimes also referred to as link editing. And a static linker such as LD is sometimes referred to as a link editor. Every program, including those that use shared libraries, goes through a static linking phase. At runtime, a program that employs shared libraries additionally undergoes dynamic linking. The shared library SO name. In the example presented so far, the name that was embedded in the executable and sought by the dynamic linker at runtime was the actual name of the shared library file. This is referred to as the library's real name. However, it is possible, in fact usual, to create a shared library with a kind of alias called a SO name. The DT SO name tag in ELF parlance. If a shared library has a SO name, then oops, I think I'm breaking my chair here. If a shared library has a SO name, then during static linking, the SO name is embedded in the executable file instead of the real name, and subsequently used by the dynamic linker when searching for the direct library at runtime. The purpose of the SO name is to provide the level of indirection that permits an executable to use at runtime a version of that shared library that is different from but compatible with the library against which it is linked. In section 41.6, we'll look at the conventions used for the shared library real name and SO name. For now, we show a simplified example to demonstrate the principles. The first step in using a SO name is to specify it when the shared library is created. So we say GC these are some weird ass arguments, man. The w-wl-so name lib bar.so option in the instruction to the linker to mark the shared library libfoo with some so name libbar.so. If we want to determine the so name of existing shared library, we can use either of the following commands. So we say read elf. So we'll do that. Read elf on our build lib test.so, and we do want to do a -d to dump everything and grep for So name. We don't have a so name. I guess you have to specify it. Having created a shared library with a so name, you can then create an executable as usual. However, this time the linker detects that the library libfoo.so contains a so name libbar and embeds the latter name inside the executable. Now, when we attempt to run the program, we see is what we'll see. We can't find libbar. Problem here is that dynamically we can't find anything named libbar. So when using a so name, one further step is required. We must create a symbolic link from the so name to the real name of the library. The symbolic link must be created in one of the directories searched by the dynamic linker. Thus, we could run our program as follows. Yep. Alright. Oh, we got some diagrams. Figure 41.1 shows the compilation and linking steps involved in producing a shared library with embedded so name, linking a program against that shared library, and creating the so name symbolic link needed to run the program. Creating a shared library and linking a program against it. Figure 41.2 shows steps that occurred when a program created in Figure 41.1 is loaded into memory in preparation for execution. To find out which shared libraries a process is currently using, we can list the contents of the corresponding Linux-specific proc pid maps file, section 48.5. Next. Current directory. So we got libfoo so, we got our program, we got the libbar so, symbolic link. LD library path is dot, process created, dynamic loader, and program loader into memory. So then we got our environment, program header. Okay. Dynamic linker examines shared object dependencies. To say I'm missing libfoo, let's pull that in. Okay. Useful tools for working with shared libraries. In this section, we briefly describe a few tools that are useful for analyzing shared libraries, executable files, and compiled objects. The LDD command lists dynamic dependencies. Command displays the shared libraries that a program or a shared library requires to run. Here's an example: LDD prog, libdemo so1. Yeah. Cool. The LDD command resolves each library reference employing the same search conventions as a dynamic linker and displays the results in the following form. For most ELF executables, LDD will list entries for at least LD Linux SO, the dynamic linker, and libc so6, standard C library. The name of the C library is different on some architectures. For example, this library is named libc so6.1. Yeah, okay. The objdump and readelf commands. The objdump command can be used to obtain various information, including disassembled binary machine code from an executable file, compiled object, or shared library. It can also be used to display information from the headers of the various ELF sections of these files in this usage. It resembles readelf, which displays similar information but in a different format. Sources of further information about objdump and readelf are listed, and then the chapter, the nm command. This is not one that I'm familiar with. The nm command lists a set of symbols defined within an object library or executable program. One use of this command is to find out which of several libraries defined a symbol. For example, to find out which library defines the crypt function, we could do the following. Man mm, and then what's the -a flag? Okay, nm-a user lib /lib star .so star to dev null, and then we say go rep crypt with a $sign and a space. We need egrep. Wait a minute, there's a libgo.so? Does Go use this? Is this the runtime for Go? GCC Go. Okay, that's for GCC, not for the Go compiler. All right, that makes sense. I'm just gonna grep out libgos. libgo. All right, we got some crypt stuff, but not much. Okay, that might just be a dated thing. The -a option to nm specifies the library name should be listed at the start of each line displaying a symbol. This is necessary because with default nm lists the library name once, and then on subsequent lines all of the symbols it contains, which isn't useful for the kind of filtering shown in the above example. In addition, we discard standard error output in order to hide error message about files for formats unrecognized by nm. From the above output, we see that crypt is defined in libcrypt library. Is there even, if I do this on libcrypt, .so, it says no symbols. If I do read elf s, it's able to find them. Funny that. Obj dump. Oh, S is decompile, right? Is cap S? No. T. No symbol table. But readelf was able to find it. Isn't that funny? Man readelf. Cap T. There we go. Yeah, all these obviously these are things that it's like referencing in other libraries because they're 0 bytes. Even these though, are 0 bytes. But these functions actually have some code to them. So this thing is probably the actual crypt function, 17 bytes. It's not that big. But one thing I'm noticing is that like all the symbols, they're always like the symbol and then at and then the library. And some of them use a single at and some of them use a double at. Not really familiar with that format. I wonder if that is like name mingling or if that's just like a C thing that I'm not familiar with. All right, let's go back over to here. We got shared library naming conventions. We got a lot to go still, and I've not made a lot of progress because I'm enjoying this so much. This might be a day where I just get slowed down. But yeah, let's continue. It's about 5. Actually, no. Let's go and stop here. And I'm going to grab dinner. And I'll get back on ideally before 6. So I'll have 6 and 7. I'll have at least another 2 hours. But I'd certainly slow down this because I wanted to play around with the linking stuff. So let's go back to progress. Go down here and we'll say 5 o'clock. I stopped at 8:44. I only made 11-page progress. Okay, and then we'll come back this evening for some more. Okay. All right. I will be back in about an hour after I get some dinner. And I'll continue reading about shared libraries, the fundamentals of shared libraries, and finish off this chapter. And then we got more advanced shared library stuff. And then we got some of the IPC stuff. So I don't know if I'll get through all of this tonight because it's just a lot of stuff. And I'm actually really interested in making sure I understand all this stuff and have time to do experiments. So today might be a day I just not hit 100 pages. But yeah, I guess I'll be back in about an hour.